In this video, we are going to go over entire chapter 3 notes. Chapter 3 deals with the topics in probability. We are going to be spending next few chapter 3, 4, 5, 6, 7 all on the topics of probability. So it's a huge topic. And then we are going to be in particularly talking about the basics in chapter 3. And then chapter 4 and 5, we are moving more into a complicated probability topics. So chapter 3, let's begin with some terms and definitions. First one, unblink, an event is an any collection or of result or outcome of a procedure. A blank, a simple event, is an outcome or an event that cannot be further broken down into simpler components. Now these two sounds pretty similar. So after I define the next two, I'm gonna give an example that illustrates all this. The blank, the sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. The complement of event A, denoted by A bar, some textbook, our textbook, the OpenStats, use A apostrophe. So you might see the A bar or A with the apostrophe. That means it consists of all the outcome in which event A does not occur. So all four definition is a bit confusing because they have a similar explanation, result of an outcome, collection of an outcome. So here is an example that illustrates all four definitions, four terms. So let's say there is a procedure and you are giving a birth. Okay, so let's create a column that has a procedure. And I'm going to create another column called event. And then I'm gonna call sample space. And then A bar or A apostrophe complement. So let's say you're giving a single birth. So that's a procedure. So there's a single birth. Event, what will be the example of an event? Well, the event says any collection of a result or outcome of a procedure. Well, in the procedure single birth, in a single birth, it can be any collection. So let's say I gave a girl. That is an example of an event. I could give a boy, then boy will be an event. Okay, this is any collection of a result. I give a birth, it's a girl. That's a result of an outcome of a procedure. Now, girl, for this example, is a simple event. It's an event, but it is a simple event. Why? This is an outcome or event that cannot be broken further down into simpler components. Well, I gave a birth, and that's it. There's no further outcome after that event. Sample space for the single birth. Sample space, the definition says, consists of all possible simple events. So the sample space for the single birth is boy, girl. So there's a two elements, two event, either boy or girl. And that's it. That's all the possible events, simple events that I could have in the single birth. Well, what will be the A bar or A apostrophe complement of event A? It is consists of all outcome in which event A does not occur. Well, event A is called a girl, so event A. Well, so the opposite or the thing that did not occur, so if you're giving a girl, then boy will be a complement. Okay, so hopefully this example kind of illustrates these four definitions. I'm gonna go ahead and give you another example. Let's just do one more practice. This time, let's say you're giving 3 births. Okay. All right, so 3 birth. I'm running out of space, so I'm going to be using actually a scratch paper on this example. So oops. Okay, let me copy this chart. All right, this was a bar, right? So 3 birth. What will be an event? Well, there's a lot of possibility. Let me just pick one event that can happen in 3 birth. So let's say in 3 birth event, so it's any collection of a result or outcome. So let's say I got 2 boys, 1 girl. Okay, it's possible. I gave 3 birth and then I got a 2 boys and 1 girl. This is an event, but this is not simple event. Not simple event. Why? Because this is an event that can be further broken down into simpler components. So for example, what do I mean by that? Well, 2 boys, 1 girl, having a boy, boy, girl is different than boy, girl, boy, right? I gave a birth, first child, I got a boy, second child, I got a boy, and then third child, I got a girl. That is different from first child boy, second child girl, and then third child boy. They both have 2 boys and 1 girl, but the order matters, and then 2 boys, 1 girl can be further broken down into even more simpler parts. So therefore, 2 boys, 1 girl is an event, but not a simple event. Okay, of course, there's more, right? I could have, oops. Also, another possibility will be girl, boy, boy. What else can I have? Boy, I have boy, boy, girl, boy, girl, boy, girl, boy, boy, and I think that's it for the 2 boys and 1 girl event. Now, sample space. What is my sample space? Sample space consists of all possible outcome. In 3 birth, boy, boy, girl, boy, girl, boy, and girl, boy, boy is not the only possibility. So let's start listing out everything. I could have a boy, 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 so all boys. I'm gonna copy down the other one that we have, boy, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. 1, 2, 3, 4, 5, 6, 7, 8. 8 possibility. How do I know that there's 8 and that's it? Well, by the simple probability rule, you know that I have 3 spots to fill because it's a 3 birth, and I have 2 choices for each. So 2 times 2 times 2 will give you 8. So that's how I know that there are 8 sample space. So complement of A will be, so it will be the opposite, the remaining one. So I have, let me highlight these ones. So BBG, BGB, GBB, I have it here. BBG, BGB, GBB, GBB. So I'm going to exclude these 3 and then write down the remaining one. So I will have BBB, BGG, GBG, GGB, and GGG. Okay, and that's it. Now, this is the fact, and I'm going to be further explaining this towards the end of chapter 3. I hope someone kind of made an observation. There's a relationship between the A bar, and the sample space, and that is event A plus A bar will always be equal to the number of sample space. Okay? Or sometimes you could write it this way to A bar. You could use A bar or A apostrophe. Same notation. Will always equal to 1 whole, 100%. Okay, so keep that in mind when we go over these towards the end of chapter 3. Okay. There are 3 types of probability. I'm going to go through those 3. So chapter 3 has a lot of terms and definition because it's an intro to probability. So there will be a lot of terms. The next one, the first type of probability is relative frequency approximation probability. This probability conducts or observe a procedure and count the number of times that event A actually occurs. Based on these actual results, PA is defined as number of times event A occur over the number of times the procedure was repeated, or sample space. Now here is our first time seeing the notation P parentheses A bar. This just means it's a notation that tells, oh, probability value of event A. They do not want to write down this whole long word, so they use a notation P parentheses A means probability value of event A happening. We have seen the relative frequency in chapter 1, I believe, or chapter 2, when we calculated the frequency, relative frequency, cumulative relative frequency. It's same concept. We simply observe something and then count the number of that event, put it on the top, and then on the bottom, the whole number, the whole sample size. So that's the same concept. Classical approach to probability requires equally likely outcomes. So this one has important part. Requires equally likely outcomes. So I'm talking about when something happens, I have an equal chance of happening. Like a birth example. If I'm giving a birth, there's an equally likely chance that I get a girl or a boy. There's exactly 50-50. Okay? Assume that a given procedure has n different sample events, that each of these simple events has an equal chance of occurring. Event A can occur in S of n ways. So again, very similar to the relative frequency, number of ways A occur over the number of different simple events. Okay, so they use letter S over N. Okay. Number 3, subjective probability. Although we do have a subjective probability, we don't use this often in statistic course because we want the actual number, but sometimes we have to have an estimated probability value. So what is a subjective probability? The probability of event A is estimated by using a knowledge of relevant circumstances. So this is just the estimated probability. Okay? There's an example on next or the bottom page and the next page that illustrate all 3 examples. Let's begin with example 1. A recent Harris Interactive survey of 10 adults in the United States showed that 202 of them smoke. Find the probability that a randomly selected adult in the United States is a smoker. So here they want you to find the probability value of what? Smoker. So probability event A is a smoker. Here, what is example 1 illustrate out of the 3 probability? Relative frequency, classical, subjective. This is an example of a relative frequency probability. Why? Well, there's this count numbers. You simply observe the data and then there's a count, the data value. You survey 1010 and then count that 202 of them smoke. So this is an example of a relative frequency. And in the description, there's no words that says equally likely. So this will be a relative frequency. And very simple, number of times event A occurs, so number of smoker. Our A was defined as a smoker, so 202 over 1010. You could leave it out this way, or you could change to a decimal, so 202 divided by 1010 is 0.2, or you could leave it out as a 20%. WebAssign might tell you to leave it as a fraction, decimal, percentage. You could also reduce this number because it's both even number into a simple fraction. However, I'm not going to be reducing down any of the fraction from now on in the topics of probability because I'm losing some information. The fraction 202 over 1010 tells you important data value. There are 1010 sample values and exactly 202 of them smoke. So they give you these two values as a data value. If I reduce down this number, mathematically the value will be still 0.2. However, I'm losing some information. So that's why I like to purposely leave it out as an unreduced form. So anytime I express a fraction, I'll leave it as an unreduced form. Okay. Moving right along to the next page. Example 2, when 3 children are born, the sample space of gender is, and then they list out all the sample space, 1, 2, 3, 4, 5, 6, 7, 8. Right. Just like I gave the example earlier. So this is a 3-birth example. If boys and girls are equally likely, I see the keyword equally likely, then 8 simple events are equally likely. Assume that boys and girls are equally likely. Find the probability. Okay, here's what I need to do. Probability. Find the probability of what? Getting 3 children of all 3 children, all of the same gender when 3 children are born. So I want the probability of same gender. Okay. And as you guys can see, this is an example of classical probability. Why classical probability? There's a word equally likely. Going back to the definition, classical approach, the number of ways A occurs, so same gender. So I need to count how many same gender I have and put it in the numerator. Number of different simple events. So they list out all the sample space, so that's nice. There are 2 events that have a same gender, which is BBB and then GGG. So that's the number there, 2 out of the sample space 8. Again, I'll leave it out as a 2 over 8, not reduced down to 1/4. This is equivalent to 0.25 or 25%. Okay. The last one. What is the probability that you'll get stuck in the next elevator that you ride? This is an example of subjective probability. First, we do not have actual data. There's no number given. It's just from our prior knowledge and estimate the probability. Now, we do have good. When you give out this estimated value, you wanna give a reasonable number. So it's not there's not that many high chance of getting stuck in the elevator, right? Think about how many times you got stuck in the elevator. Not so much. Also, if you live in an apartment complex that do not have an elevator, you have even lower chance of getting stuck in the elevator because you do not ride the elevator every day. So that's why it's subjective, because it all depends on people and their situation. So the text, so I think even putting like 50% is too high. Even 10% is too high. That means every 10th elevator that you ride in your life, you get stuck one time. The textbook gives this number 1 over 10,000. So yeah, that's really, really small. It's a rare event. But I'll stick with the textbook subjective probability value. But I think even 1 over 1,000 will be a reasonable answer too. But this is the answer for the textbook. So those are the 3 types of probability. Okay. All right. Let's continue with a few more terms and definitions. A blank, an event is unlikely if its probability is very small, such as 0.05 or less. So you calculated a value, the probability is less than 0.05, we call that event unlikely to happen. Going back to this example 2, I have a probability 0.25. That's bigger than 5%. So this is likely to happen. Having a same gender, that's likely to happen. An event has an unusually low number of outcome of a particular type or an unusually high number of those outcomes if the number is far from what we typically expect. Kind of like our outlier when we talked about the data, low ends and then high ends. So you have this low number of chance of getting that event happening, and then there's a high chance of event A happening. The blank, the actual odds against event A occurring are the ratio PA bar over PA, usually express it as A to B ratio, A to B ratio. The blank, the actual odds in favor of event A occurring are the ratio PA over PA bar. So ratio, it's a ratio, so you see the fraction value. PA bar over PA, and then basically actual odds in favor will be the reciprocal. PA on the numerator, the probability over probability of A bar. The blank, the payoff odds against event A occurring are the ratio of a net profit if you win to the amount of bet. The payoff odds against event A will be net profit to amount bet ratio. These last 3 are terminology used typically in gambling. Okay, what are my odds against winning blah blah blah? What are my payoff odds? Okay, so those are typically used with gambling and then the casino games. Okay, so I have a next example that practice the last 3 definitions. If you bet $5 on the number 13 in roulette, your probability of winning is 1 out of 38, and payoff odds are given by the casino 35-1 ratio. Find the actual odds against the outcome 13. Okay, so find the actual odds against the outcome 13. So A is that 13, outcome of a 13. So betting the number when you begin playing roulette and then it landed on 13, that's event A. A bar will be everything else, right? A bar was a complement, so not an outcome of 13. Okay. Actual odds against the outcome. Actual odds is defined as PA bar over PA. PA bar over PA. So P of not of 13 over P of 13. Okay, so there's two numbers, top number and the bottom number. Let's first calculate the probability of not having a 13. Well, if you bet $5 on number 13 in the roulette, the probability of winning is 1 out of 38. Where's that number 38 coming from? If you are not familiar with the game of roulette, roulette has 38 spaces where you can make a guess, and then the dealer roll a ball, and then wherever it lands and you guessed it correct, you win. So there are 38 places to make a bet. So not a 13 will be 37 out of 38. That's your probability. Having a 13 will be 1 out of 38. Now this is a fraction over fraction, so we do not like fraction over fraction, so I'm gonna simplify a little bit further. Okay. We have, I'm going to be multiplying both the numerator and the denominator by the reciprocal, so 38 over 1, 38 over 1, reduce, cross cancel, so I end up having 37 over 1. This is a ratio, so it's possible that you can have more than one, okay? So this means we have a 37-to-1 ratio. Okay, so the actual odds against the outcome 13 is a 37-to-1 ratio. How much net profit would you make if you win by betting on 13? Net profit. What is a net profit? Well, net profit is the pure profit, right? You bet $5 and then payoff odds is given by 35-to-1 ratio. Going back the payoff odds definition, payoff odds, the first number is a net profit ratio, and then the second number is the amount of bet. So we have a payoff odds given from the problem as net profit amount bet as a 35-to-1. So that means if you bet $1, then you are going to make pure profit of 35. Well, you bet $5, so let's switch the number. So if you bet $1, you get 35. So your net profit for winning will be $35 times the $5, which will be $175 net profit. Now the term total, you made $175, but you're technically are not receiving $175. You will receive $180 total from the dealer. Okay, why? Because they need to give you back your original $5. So net profit is at $175. The total amount that you will receive is $180. Okay, but this will be the final answer for this particular example because they asked for net profit. But be careful with the wording of the question. Make sure that profit is either, be careful reading that because it may give you the total or the net profit. Last one, if the casino was not operating for profit and the payoff odds were changed to match the actual odds against 13, how much would you win if the outcome were 13? So the payoff odds got changed to match the actual odds against 13. So it was a 35-to-1 ratio, but now it got changed to the part A, 37-to-1. That was the actual odds against the outcome 13, 37-1. So now your new rate is a 37-1 ratio, which means this is your net profit, this is the amount to bet, which is a better, right? Your net profit got higher. So net profit versus amount to bet. So we have a net profit of that 37 times $5. Then this time you're gonna make 185. Okay, 185. Okay, all right. So that's 3.1. Let's move on to 3.2 and 3.3. Okay, so this is the last part, or we have 3.4 as well, but this is kind of like second part of the probability. Now in these sections, I'm going to start giving some formulas of how to calculate the probability. 3.1, we are talking about individual event, one event happening. However, you could have more than one thing happening. So that is called a compound event. A compound event is any event combining two or more simple events. Events A and B are disjoint or mutually exclusive if they cannot occur at the same time. So now you have PA or B, right? You see that not just PA or PB separately, you have two events combined. So PA or B is calculated as a P of A plus probability of B value, subtract probability of A and B. Let's think about this. Where's this formula coming from? Well, let's say you have an event A, and here's an event A, and here is, and here's event B. When I say A or B, that means something can be A or it can be B. So it can be, the answer can be in A, and then the answer can be B. Okay, right? Now, so the answer to A or B is this entire set, right? The red part and the blue part. However, it's not just A plus B. When I shaded in the red and the blue, there was an overlap, and I counted technically twice when I shaded red and then also the blue one. So there's the double count of where they intersect A and B. So I need to subtract that part here. So that's why you have that subtraction PA and B. PA and B is that overlap there. Okay, so don't forget to subtract. So P of A or B is P of A plus P of B. Subtract P of A and B. Adding in such a way that every outcome is counted only once. The second part, P of A plus P of A bar is equal to 1. Okay, this is the one that I mentioned it. You have an event A, and then A bar will always make up the whole thing. So same thing, probability of A and A bar will be the same. Now, this is equivalent to, by algebra, there's an equation, so you can kind of switch around. So if you have P of, I'll write it down over here. If you have a P of A plus P of A bar equal 1, let's say I subtract P of A bar, then I can also subtract P of A bar on the same side, and I'm not changing any value. Then I have solved P of A as 1 take away P of A bar. So I could have P of A also equal to 1 whole thing subtract P of A bar. So that's another modification. Okay. it means the same thing. Sometimes this might work better, sometimes this might work better, depending on what you're given. Also, you have P of A plus P of A bar. Now, let's say instead of subtracting P of A bar, I subtracted P of A this time. Then you're basically solving P of A bar is equal to 1 take away P of A. Okay, so that's that. P of A bar is equal to, let me erase this part here. 1 take away P of A. Okay. So make sure you guys are okay with this format. First format, second format, third format. They're all same thing. Example, based on data from a Harris Interactive poll, the probability of randomly selecting someone who believes in the devil is 0.6. So P of believes in the devil is 0.6. If a person is randomly selected, find the probability of getting someone who does not believe in the devil. So this is basically, here's PA. I'm talking about P of A bar. So P of A, which is defined as believes in the devil. And it's also given as a 0.6. Then it's asking P of A bar. By the complement, so this is when you use the complement rule. You know that PA plus PA bar will equal to whole thing. Not believe in the devil. So in other words, you know P of A, I can use the second formula and get the answer right away. P of A is 0.6, right? 1 take away P of A bar. Oh, actually, I think this last one is better because I'm solving for P of A. Let's use this one instead of the second one because I have to do some modification here. So using the last equation, P of A bar, because we are solving for P of A bar, 1 take away P of A, which is 0.6, I have 0.4. So 0.4 will be the final answer. Now, addition rule, we have two formulas. I'm going to highlight it for you because I'm going to reference back to these a lot. So there's two addition rule. Multiplication rule, we have two formula as well. Here we have this coming up. So I'll talk about multiplication rule of a probability. Before we get to that, let me define the two terms. Two events A and B are independent. If the occurrence of one does not affect the probability of the occurrence of the other. If A and B are not independent, they are said to be dependent. So what does that mean? Independent is there's a first event. Now the second event has nothing to do with the first outcome of an event. So they are separate. However, dependent means first event occur and then the second event does get affected by the outcome of a first event. So another word instead of independent event, you might see a description that says sample with replacement. And then dependent is a sample without replacement. Because think about this. Let's say you have a 10 sample. I need 2 volunteers, so I have to randomly draw the 2 people. Let's say I pick the first sample, okay? And then that sample do not get picked again. So the second people that gets picked as a volunteer does get affected by the first result, because now I don't have a 10 people in the pool, I have a 9 people to choose from. So there's a sample without replacement. Let's say I have a ball in a box and then I'm drawing 2 balls. First ball, I'm looking at the outcome. Oh, it's a white ball, okay? And then I put that white ball back to the box, and then I draw the second ball. Oh, it's a yellow ball. Then it doesn't matter about the second ball. The ball always remain the same. The sample does not reduce. Each time it's always that same sample size. So it doesn't matter which ball that I choose, you're always going to have a same occurrence. Okay. Don't worry about this one here, second bullet point. Smaller sample with the less than 5%. We think of it as an independent, but it's just, let's make the independent and dependent separate event. Independent is a sample with replacement. Dependent is a sample without replacement. Okay. P of A and B is defined as, now do not get confused. I know the textbook uses the same word with this here. This P of A and B with this P of A and B. Okay. The first P of A and B from the addition rule comes from that intersection A and B. Whereas P of A and B in the multiplication is just event A and then B for the second event. Okay. How do we calculate the probability event A and then second one event B? Well, for independent, it will be PA times PB. Second one, PA versus PB bar A. That's the dependent one. This is called conditional probability because I talked about that dependent does occur. The result does get affected by the event A happening. So there's that PB bar A. Okay. I'm going to give you an example because that looks a little bit confusing. So let me add another page. Okay. So going back, so we have a P, A, and B defined as PA versus PB. This is a formula for independent events. And then P, A, and B defined as PA with probability B condition on event A happening. Dependent event. Okay. Let me put down a little bit here. So here is a ball problem, going back to the ball problem. Let's say in a box, okay, I have 5 black balls, okay, and then just making a number, 2 white balls, and then 3 green, and then another 5 yellow balls. Okay. Let's say I want the first ball, so event A is green. I want the green, and then B is yellow. Okay. Then let's say this is an independent event. Then P of A and B, P of green and yellow the chances of having that green and yellow will be, well, first one, you have a problem, and then the sample size in this space is 5 plus 5, 10, so it looks like 15. Yeah, 15. Well, independent event will be probability of green times probability of yellow. Well, probability of green is, there are 3 chances out of 15, right? You draw a ball, the probability of green is 3 out of 15. Yellow will be 5, still out of 15. Why? Because it's an independent event, sample with replacement. So even though I took out a ball, I checked that it was green, I'm gonna replace back. So your sample size do not get reduced. It will be always out of 15. So it will be 15 out of 15, which is equal to, not 15, 15 out of 15 square. It's 15 times 15. So the chance for having a green on the first one and then yellow on the second ball will be 15 out of 225. Okay. Versus, let's say this was dependent event. So the problem will tell you, oh, this is a dependent event or sample with without replacement or with replacement. Then how is that going to change? Probability of still green and yellow is defined as probability of green and probability of green, probability of second one, I want yellow, but assuming that the first one already occurred with the green and without replacement. So green, the first one doesn't matter, it's still out of 15, 3 out of 15. Now this time the yellow will be 5 out of not 15, because this is the conditional, it will be 14. So your answer will be 15 out of 15 times 15, 14 to 10. Okay, so that's the difference between independent and dependent events. Okay, here's more example problems. So let's work on the next example. A study on the effect of new drug shows that 44 subjects have positive test result, and 6 subjects have a negative test result. If 2 of the total number of subjects are randomly selected with replacement, so there's my key word, with replacement. What is with replacement mean? It's independent. The total sample pool does not reduce. Independent. Find the probability that first selected person, that's your event A, positive test result, and then second is a negative test result. So I want probability of positive test result, PTR, and the second one to be a negative test result. This is an independent, so it will be just a simple one, PTR times probability of NTR, no conditional one. So I just have to calculate the probability for each and then multiply out. What is the probability that I'm having a first picked and that's a positive test result? Well, there are 44 of them out of 50. Where am I getting 50? 44 plus 6 will equal to 50. The second one, I want the sample to be negative test result, so it will be 6 again out of 50 because it's an independent event. So 44 times 6, 264 out of 50 times 50, which is 2,500. You can leave it out this way, change to a decimal, that is 0.1056 or about 10.5%. About 10.5% chance. Part B, repeat part A by assuming that the, typo, that's a 2 subjects, are selected without replacement. So that's the only difference. I still want the positive test result, the negative test result, but without replacement, which is the dependent. We have a PTR and NTR. I want positive test result for the first one. I want the negative test result condition on that positive test result. Dependent one, the 50 number of subject reduced once I go to the second event. So 44 out of 50 times this times 6 out of 49. So that gives me 0.1078. Okay. Last page. Contingency table. This is just another way of calculating. First one and second one, we actually talked about this a little bit when we were talking about that addition rule and the multiplication rule, but they further elaborate those two. That probability of at least one is very similar to this the complement idea, and then the conditional probability actually comes from this part. I told you that this part is a conditional probability, so they kind of basically solve PB bar A. But let's go back, starting with the first bullet point. A contingency table provides a way of portraying the data that can facilitate calculating the probability. The table helps in determining conditional probability quite easily. The table displays sample value in relation to two different variables that cannot be dependent or contingent on one another. This is an example of a contingency table. Basically, it's a display of a table that tells you the data value, and it helps us calculate the probability more faster rather than reading through the whole conditions. Probability of at least one. What is a probability of at least one? At least one, when I say at least one, this means same thing as one or more. Something happening, event A, one or more. I want at least one green ball. That means when I draw a sample, doesn't matter how many size of a sample that I need to have at least one or more green balls, right? So that same thing as saying the complement of getting one, remember complement is opposite. If you want one or more, then the opposite means no occurrence, nothing. So you could say probability of at least one could be divided by the whole thing, take away nothing will give you one or more. So there's that equation, 1 minus PA bar. Okay. Conditional probability. Find the probability of event A occurring when we have additional information that some other event has occurred. This is just a equation that comes from here. They just solved it for you. So you have P of A and B from the dependent event defined as a probability A times probability B bar A. Now if I want probability of B bar A, by mathematically I can divide the whole thing by P of A. Then you have probability of A and B over probability of A as a probability of B bar A. That's it. That right there is this part over here. PB bar A is equal to PA and B over P of A. So don't think of it as a two separate formula. It's the same thing, but they just solve this conditional part and call it a conditional probability. Just like I give you the 3 different ways to write down the complement, but they are all same thing. That P of A bar equal P of A times P of B bar is the same equation as PB bar A equal P of A and B over P of A. If you make random guesses for 10 multiple choice test questions, each with 5 possible answers, what is the probability getting at least one answer correct, given that the first 9 answers are wrong? Now, this is a little bit confusing, or some people might see the answer right away. It's an obvious answer, or some people might have a second thought. Well, you are looking at probability of at least. You see the word at least, so I'll be using this formula here. At least one answer correct. So what does that mean? That same thing as one takeaway A bar. What's the opposite of at least one answer correct? Nothing. Not getting it correct. Probability of not getting correct. Okay, not getting correct. Oops. Okay. Well, what is a probability of not getting the answer correct? Here is what makes it a little bit tricky. This information about the 10 question is to trick you out. 10 multiple choice test question. Well, why? That 10 has nothing to do with answering the not getting correct, because they already told you that the first 9 answers are wrong. So you have number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 question. All these answers are incorrect. So the last one is the one that matters. And then I want that at least answer correct. So that means I better get this one correct. So not getting that answer correct will be 4 out of 5. So why? Because there's 4 choices. So I need to put 4 out of 5. By fraction, addition, subtraction, you need a common denominator. 1 is equivalent to 5 over 5 minus 4 over 5. So it will be 1 out of 5. Now, this is kind of a long way of answering the question because I just wanted to use the formula and how it's used. But you can kind of use a common sense and then get the answer 1 over 5 right away. Because think about this. Okay, I got all the question wrong except the last one. In order for me to get that question correct, because I want at least one answer correct, is I better get this one correct. Then there's 1 out of 5 chance if I guess. So the answer will be 1 out of 5. So that's a more easier way to do that. But feel comfortable doing the homework problems using the formula, because homework problems are a little bit challenging. Okay, I always put the homework question a little bit more detailed one so that you guys are having the practice, not always the easy one. So make sure you're okay with using the formulas. Okay. Last one. The table below show pre-employment drug screening result, and there are those 4 numbers with the 4 cases. If one of the 1,000 test subject is randomly selected, where's the 1,000? 44 plus 6 plus 90 plus 860. Yep, that's a sample size of 1,000. Find the probability that the subject has positive test result given that the subject actually uses drug. Here you have to feel comfortable reading this question and writing into a notation. Word given that is the conditional part. So you might see the word given. Given that first event occurred, given that this happened. So that's a conditional probability. That's a keyword. Okay, so again, there's a more easier way of getting the answer right away using the chart, but I'm going to purposely use this formula here so that you guys feel comfortable using the formula as well. Here's your B, here's your A. Always the B first and then A. Remember, because A happened after the B, A happened before the B, so PB bar A. So B is your positive test result, A is your subject using the drug. by the definition, P B bar A is defined as P A and B over P of A. So probability of subject uses drug and positive test result over probability of subject using drug. Well, what is the probability that someone is subject using the drug? So getting that number, I need to look at the first row because first row has a subject using a drug. And at the same time, positive test result for 44 out of how many? 1,000. Subject using the drug, that will be this whole column here. So it will be 50 out of 1,000. Multiplying 1,000, multiplying 1,000. I'm getting 44 out of 50 or approximately 0.88, 88%. Okay. All right, this is pretty much it for chapter 3. When we go to chapter 4, we are going to look at probability function in terms of mathematical format. Okay.